and welcome to the Daily Space for Tuesday, June 5th, 2018. As always, I am your host, Dr. Pamela Gay. Well, it's not actually as always. We periodically have Andres Plazas also stepping in, and I'm sure there will be some day this week that he steps in. So welcome, everyone. I'm going to bring you a roundup of all that is new in space and astronomy, or at least an edited version. This week, we have the American Astronomical Society meeting taking place in Denver, Colorado, and there is more news than you can, well, point a telescope at. So let's hurry up and get started. And I had to do a rather quick reboot before we start, so I have to fix my layout. There we go. So there's certain stories that we get on a regular basis. This is basically institutions realizing, ooh, this is cool, this is newsworthy, people will want to know this thing, and not realizing we already know this thing, but not with the same details. Astronomy and most sciences are all about discovering new details. We hear mostly about the breathtaking work that is taking place at the edge of understanding, the finding of the new worlds, the new types of galaxies, the new types of star collisions. But most of us scientists were working on the details to fill in the gaps between these big, breathtaking discoveries. And one such news story comes to us today in a recent reconstruction of our understanding of the relationship between our own Earth and its moon. Scientists have gone beyond simply working on modeling to digging through the Earth's past by digging through its rocks. We've known for a long time that historically, by which I mean eons ago, our Earth rotated much faster. It turns out our Earth used to actually have what we would now call an 18-hour day. In this past, our moon was a lot closer. We didn't really have annular solar eclipses because, well, the moon had an easier time blocking the sun. And humans weren't really worried about getting more hours added to their day. But the moon has been adding those hours over the eons. In new work that has come out from the University of Wisconsin-Madison, scientists, including Steve Myers, have gone through and not just looked at the computer models for how the Earth-Moon system has evolved, but they've also gone and looked at what is the geophysical record. Can we get at time via rocks? And the answer was yes. And they've been able to confirm and add details to our understanding that as the moon moves away from the Earth, something that we can measure with lasers, such as the laser distance ranging system they have down at McDonald Observatory in Texas. By shooting lasers off the moon, we can very carefully measure the amount of time it takes for that light to travel from the Earth to the moon. And we can see from year to year how the moon is slowly migrating away. With it, thanks to conservation of angular momentum, our own Earth is slowing down in its rotation. So, more details. We have more details, and now you know more hours in the day are coming. We're just not going to live long enough to see them. Now, moving a little bit further out, I have an update on a story from a few weeks ago. As I'd previously let you know, the Jet Propulsion Lab out in California, located on the campuses of Caltech, had figured out how to change the way Mars Curiosity rover works so that they could work to get its drilling arm back in service. Back in October of 2016, all mission science related to drilling holes and picking up samples had to cease because the drilling arm just wasn't working the way it was supposed to. As designed, this arm had a pair of bumpers that went out, extended against the surface that was going to get drilled into, and stabilized the drilling platform. Unfortunately, this situation, as designed, was no longer functional. In the intervening months and years, teams out at JPL have worked on a duplicate of this arm to figure out how to get it working in a way it was not designed to work. And they took a page from how humans drill things. And what they decided to do was just extend that drill all the way out, lean on it with the arm, and drill that way. It's more brute force, more how you might do things in your garage, and it turns out it works. They have now been able to drill, and in a press release that came out today, we have news that they've been able to gather a sample, drop the rock powder into the rover for analysis. And now, once again, we are able to actually use the ovens and mass spectrometers all on board this little rover that can to figure out what Mars is made of. So this is an exciting bit of engineering news, and now we stay tuned to see what science will come of it. Now, while I don't think this is entirely related, NASA has announced that on Thursday at 2 p.m. Eastern, there is going to be a press conference, which they will be streaming, and we will try to bring to you with commentary here on CosmoQuest X. There will be a press conference on new Mars Curiosity results that are getting published in the journal Science. So stay tuned until Thursday afternoon, afternoon here in the United States, when we can bring you updates on science coming from Curiosity. Now, looking a little bit further out in our solar system, there was an accidental discovery in software written by an undergraduate. It's actually strangely not as unexpected as you might think for things like this to happen. I have to admit, my own very first research paper came from me not knowing what variables my advisor wanted me to plot, so I plotted everything and found a scientific trend he didn't know to look for. Because why would you plot those two variables? Well, why? It's because I was an undergrad. In even more interesting work done by an undergrad, Jacob Fleissig, an undergraduate in astrophysics at the University of Colorado Boulder, was developing computer simulations to explore the dynamics of objects orbiting in highly elliptical orbits through our solar system. So these are objects like Sedna, shown here in this image, which is a very ruddy, reddish colored icy object that comes in close enough to be seen and then dances out towards the outer Oort cloud of our solar system. Objects with these remarkably elliptical objects aren't very common in our solar system. At least they haven't been commonly detected in our solar system. In writing software to try and better understand how these objects interact with one another and interact with objects in the Oort cloud and the Kuiper belt all around our solar system, Jacob turned up some interactions that may have an interesting side effect. While not actually looking for a new way to explain why it is that so many minor planets in the outer solar system all have elliptical orbits pointed in the same direction, he may have actually run a simulation showing that interactions year after year, eon after eon, through the centuries may just have the capacity to, like ping pong balls, bounce everything into one particular direction. This code, which has been reviewed by his advisor, Assistant Professor Anne-Marie Madigan, may offer up a new theory for all of these elliptical oddities. And this may mean that we don't actually need Michael Brown's theorized Planet 9 to explain why we see the orbits we see. Now, I have to admit, this is one research paper that I'm hoping that on further review, on further features being added to the software, goes away. It wouldn't be the first time we had a model that, as we added details to it, stopped showing what we thought it was showing. But if that doesn't happen, we may not need to go find another big planet in the outer solar system. We may simply need to look at how over time planetary interactions can drive things in to highly elliptical orbits. This is a mystery of resonance and gravity, and only time and telescopes and better data processing will help us understand who is right. The team at CU Boulder, looking at computer simulations that may explain elliptical orbits through minor body interactions, or Michael Brown and his colleague who are looking for another world. I really want another world, but science doesn't care what any of us want. Rather, we all have to just wait and see what the data tells us is true. Now, looking even further out, I have another story on globular clusters. You saw this picture yesterday, and this is because it turns out people writing papers on globular clusters don't necessarily include shiny pictures. This is an image taken by the Hubble Space Telescope, and it's a picture of a standard globular cluster. And in new results, we are getting a new picture on exactly what globular clusters may be. Now, over the course of the past couple of decades, we have gone from thinking that globular clusters were the oldest thing in the universe to realizing they're not quite that old. There was actually a point in time where our observations of the Hubble constant, the rate at which our universe is expanding, and our measurements of stellar evolution looking at globular clusters had a discrepancy that made it look like globular clusters were older than the universe. Now, we knew this wasn't true, and we kept modifying our theories. This is where I told you, sometimes upgrading your code, updating your theory can update your science. With updates to our understanding of stellar evolution, with refinements to our measurement of the expansion rate of our universe, we were able to wrangle the age of the universe up and the age of globular clusters down until we had a universe that made sense with stars younger than the universe. Now, we still thought globular clusters were one of the oldest things. At least our Milky Way galaxy's globular clusters were one of the oldest things in the universe. But in new work done by folks at Warwick University, they have been studying the interactions of binary stars in globular clusters. And in trying to understand exactly what kinds of binary stars can be present, looking at the way these two stars in one system can affect each other's evolution and appearance, they're models from the binary population and spectral synthesis models. I actually downgraded the age of globular clusters even further. It turns out these systems may actually be 9 billion years old instead of the previously thought 13 billion years old. Now, if these models prove out to be true, this means that we don't actually fully understand how galaxies form, which admittedly we knew, still filling in the details, but it means our timeline is wrong and that globular clusters could have co-evolved with our early galaxy. So more data is needed, more models are needed, and perhaps a new way of viewing our universe is needed as well. Now, those are the big stories for today. I'm probably going to need to do a massive news roundup at the end of the week as we run out of, well, time to present everything that's going on. I may actually do that roundup on Thursday, so be prepared for Thursday to be a significantly longer episode of The Daily Space. Now, right now, actually today we don't have something following up, so I'm going to go ahead and say, what are your questions for today? If you could @ me in the chat, it will make it easier for me to find your questions. Thanks for watching. Once again, this has been The Daily Space. I am Dr. Pamela Gay, and this project is brought to you by CosmoQuest. Visit CosmoQuest.org, where you can learn and do science. We have a particular call for help analyzing images of Mars and Mercury right now. So if you go to CosmoQuest.org during a spare stolen moment or two, you can map out craters and other features on these rocky worlds and help us better do science. Now, CosmoQuest and The Daily Space are all part of the Astronomical Society of the Pacific, a 501c3 nonprofit. We are supported thanks to you. Every subscription and every bit helps. Give us a follow and find out when we go live. Our next stream will be tonight at 9 p.m. Eastern, that's 6 p.m. Pacific, and 11 a.m. Friday if you're in Sydney, Australia. So, thanks again, and shoot me your questions. I'm going to go ahead and switch screens so that I can see things a little bit better. Now, I think I saw something. Yeah, there's a bunch of stuff in here. So let me see. So Larry is saying, does that mean that population 1 stars in these clusters? No, these are not. So we base whether or not a star is what we call population 1 or population 2 off of how much metallicity is in these objects. Our current generation of stars is population 1. And as we go backwards in time, we start talking about population 2 stars are an older generation or just a more metal poor generation. So these are stars that are formed out of, well, less dead star stuff from supernovae that is getting recycled into new stars. As we go back to even more metal poor stars, we're looking at what we call population 3 objects. These are stars that are made out of the earliest fast dying massive stars that actually can't even exist today. So the population type, population 1, population 2, population 3, in general refers to older versus younger, but more specifically, we judge if something's a member of one population or another simply based on what is the star made of. So population 1 stars are made of a lot of metals, which in astronomy means everything heavier than helium. Population 2, they have fewer of these heavy atoms. And population 3 have the fewest number of heavy atoms of all. Scrolling through. So Wednesday is when Matt and Joe are going to introduce a new show. Instead of having our standard office hours that we've been offering for the past few months, we're going to transition over to instead offering you an Astro 101 course. Some of our programmers don't know a whole lot about astronomy because they are programmers. But we have the ability to change that. So Matt Richardson, who is one of our project PhDs, is going to be offering Joe and you a chance to learn Astronomy 101, starting with planetary science. So I see Hanny is asking, does the change in mass of neutrinos have anything to do with the Heisenberg uncertainty principle? No. So the Heisenberg uncertainty principle says that we can't entirely know how fast something is going, know its momentum, and we can't entirely know where something is located. There's always going to be a certain amount of error in this. And part of this error comes from the wave-particle duality, this fact that something is both simultaneously a wave that isn't totally located in one place and a particle, which is more or less located in one place. So I can either tell you how fast that wave is propagating through space, or I can tell you the exact location of that particle in space, but I can't tell you both exactly at once. This uncertainty has to be built into all the measurements we make at the subatomic level. But when it comes to the mass of neutrinos varying, this is simple conservation of energy. Mass and energy are basically the same thing. And with neutrinos, they're able to convert their kinetic energy of motion, a little bit of it, into changing their mass, or speeding up by converting some of their mass over into energy. So this slight variation is just a change of state. It's just taking advantage of E equals mc squared. I don't know about you, but a lot of times while traveling, I wish I could convert some of my mass into velocity and get someplace a little bit faster while fitting into my airplane seat a little bit better. So looking for further questions. Larry has Mercury with a question mark after it. Mercury? I don't know how to respond to that. More words, please, Larry. So Peter is... So Peter, you know, another way you can really support us is just go map Mars and Mercury, or help spread the word. Well, we really appreciate subs and bits. There's lots of other ways to help us. Help us by doing science. Help us by increasing the number of viewers out there. Help us just by all the volunteer things that folks are doing to help us through the weekly Space Hangout crew. We exist thanks to volunteers who do a myriad of different tasks. Paranor being out there smiting trolls, Keeper of Maps being out there smiting trolls. All these different activities, they make it easier for us to do our jobs. And that means we don't have to spend as much time doing our jobs. And that is worth more than money. So yeah, we're old dead stuff. We are worm food, but stars aren't worm food. Stars are future human stuff. So when stars die, they make what we need. So Apita is saying, when would Astro 1 take place? It's going to start Wednesdays at about 12:30 when we're done with the daily space, and Fridays at about 12:30 when we're done with the daily space. So this show will lead straight in to Astro 101. So Peter is asking, what do you think on Planet 9, the old planetary system, or this new theory about gravity? So this new theory hasn't been as rigorously beaten up as the work that was done out at Caltech. This is because, well, the team out at Caltech looking for Planet 9 knew that when they presented this idea, it was going to generate a whole lot of detractors trying to find every other possible way to explain the motions that are seen. Having already survived that rigorous war on ideas for several years, part of me is leaning towards that being true. Now, that isn't to say that the models being done at CU aren't just that next generation of better and found something that no one has found before. It comes down to a matter of, what do I want to believe is true? Well, what I want to believe is true is that there's another planet out there. What is true? Only data can say that. Until we have data, it's only belief. So I want there to be another planet. I have a bias. So Hanny is asking, how does the Earth still have any radioactive elements since it was built billions of years ago? So any particular given atom of a radioactive material can decide, I'm going to decay right now, or I'm going to sit here resolutely refusing to decay. This is why when we talk about half-lives, we're talking about probabilities. If I start out with 1 kilogram of something with a half-life of 1,000 years, 500 years from now, it is probable that 0.5 kilogram of that is going to have undergone radioactive decay. Now, that doesn't mean that's happened. Our planet has so much radioactive material built in to its materials that, well, not enough time has passed for all of those atoms to have decided, and I shall decay now. So the probability says some of those atoms should still be hanging out, hanging on, saying, I refuse to decay. And at the same time, like I said, it's a probability that any one given particle will decay. And individual particles may last longer or shorter. Results may vary. So since we started out with enough stuff to last for billions of years, we still have stuff decaying. And this is why, if you live in an area with granite, you should do radon detection in your basement. So Larry is asking, not mapping the moon. You're welcome to map the moon. But our scientists who are working on studying Mars and Mercury really, really want their data now. So since they are saying, please, 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 data, please, please, I'm going to advertise those projects and encourage you to help these people get the data they so desperately want. Our moon team, it's more sitting back. They're good when their data comes. So let's slow down one pipeline and speed back the others. Looking for more questions. So the gravity work is totally feasible. The models that were done up at CU Boulder are a completely feasible way to explain all of these weird elliptical orbits that we see. That doesn't mean that's the correct explanation. It doesn't mean there aren't multiple explanations. It doesn't mean there isn't an explanation that no one's come up yet. Again, there are many possible things that could be true, but until we have sufficient data, we don't know what is true. So, Henny, it's not that there's just a lot of KBOs, it's that there are Kuiper belt objects, Kuiper belt objects that are lined up just right, that as they fly past each other, they, well, constantly bump one another's orbits until they end up in the resonance that we see right now. So scrolling through. So we are out of time, and it looks like we are out of questions. So this played out just right. Thank you for coming today and being with me as I share all that is new, or at least a sampling of what is new in astronomy and space science. This has been the June 5th episode of The Daily Space, a production of CosmoQuest. We are part of the Astronomical Society of the Pacific, and we will be back putting more science in your brains tonight when I return to this channel at 9 p.m. Eastern. That is 6 p.m. Pacific, 11 a.m. Friday. Thank you for the bits. 11 a.m. Friday. If you are in Sydney, Australia. Now I need to say thanks to a bunch of people. Thank you for the bits, Keeper of Maps, and thanks for the host over, Uncle Bill. So join me tonight as I continue working on a data visualization that, or right now it's mostly just a visualization of a hot Jupiter orbiting a hotter star. I will be talking the science and writing the code to help you understand our universe just that much more. I'll hopefully see some of you tonight, and wherever you are, have a great morning, evening, or afternoon, and remember to look up. Bye-bye.